Okay, we're going to look at another definite integral here. And even though this doesn't tell us to sketch the region, that's not a bad idea to do, just to think about it and make sure your answer makes sense. So I'm just going to do a little sketch over here just to make sure that we're thinking through what we would get here. So we're interested in the function y equals e to the x. So we know what that looks like. Rough sketch of that, right? This is at 0, 1, and we know what the basic shape of the exponential function looks like. We're interested in this function on the interval from x equals 0 to 3. So 0 to 3, this is just a rough sketch here, not to scale. And so we would be interested in the signed area between that function and the x-axis on that interval. So we're interested in this region right here. So just based on my picture, remember this picture is not to scale, but if I think about the y-coordinate at this point right here, when I put in x equals 3, I'll get y equals e cubed, which is a pretty big number, right? E is about 2.7, so if you think and just ballpark estimate 3 to the third, 27, so this is going to be less than 27, but that's a pretty big number. So I should be expecting a fairly large positive number for my answer here. All right, so this integral is going to represent this signed area of this function on that interval, and so we should expect a positive answer here. This is not a region I know how to find the area of just using basic geometry, but that's the point of this. What we're working on now is that we can use calculus and we can use antiderivatives to help us find the area of that region. All right, so fundamental theorem of calculus says that if our function y equals e to the x is continuous on the interval a to b, or in this case 0 to 3, this function's continuous everywhere, so certainly on that interval. And I have any antiderivative of this function. So I need to think about antiderivatives of e to the x. That one should be easy. It's the easiest possible antiderivative. Antiderivative of e to the x is e to the x plus c, if I want to talk about all the antiderivatives. But fundamental theorem of calculus just says any antiderivative, so I can use c equals 0. And then this integral is going to be equal to that antiderivative evaluated from 0 to 3. And so then I'm just going to put in my endpoints here, the top endpoint, top limit of integration here first, e cubed minus e to the 0. Right? E to the 0 is 1. E cubed does not come out to be a nice, pretty whole number. So in exact form, I can leave my answer like that, in exact form. Just to get a decimal approximation to make sure it makes sense with our picture, you might want to do that. I think you get about 19 here. If you plug that into your calculator, e cubed minus 1, you get about 19, which should make sense. I should expect a fairly large positive number for this area of this region here. All right, so fundamental theorem of calculus. We'll look at another example where finding the antiderivative is a little bit harder, but that's the basic idea with everything that you're supposed to be working on for section 5.4.